Alright, so it's around time. Let me know if you can hear it. It's 11:30 p.m. in Japan time. So I would like to start the tutorial live for this week. And so this is Junichiro Horikawa, and this is the weekly tutorial live for Houdini that I've been doing weekly, using some algorithmic design method to create some setup in Houdini procedurally. Alright, sorry for the last week I couldn't do one, so I was a bit busy. So, so this is the 87th episode for the Houdini Algorithmic Live. Hopefully I'll be able to run through at least 100 within this year. Alright, so today's topic, I don't know if you can hear it, hopefully. Okay, so today's topic is to create some setup for Houdini to create this a grid distortion using a normal grid as well as some attracting points underneath of this grid in order to create a distortion on a grid. Okay, with some parameters you can control to change some patterns, like the type of the grid. You can use any kind of grid geometry. You can also run this on top of a three-dimensional geometry as well, like this one, if you really want. That is because the underlying algorithm is pretty simple. What is going on here is that first you prepare some grid as a geometry. Let me, like this one. And then you also have this points which moving around the space, and each point has this radius value to affect on a grid for distortion. So combining this grid geometry as well as these moving points which has some radius attributes top of it, and using as an attractor, you'll be able to create this kind of grid distortion with just one wrangle. Okay, so that's what I'm gonna do, and that's pretty simple. The rule here is pretty simple. So let's do this from scratch. Hopefully I'll be able to finish this within an hour or so. Okay, so first thing first, I am going to create a grid. I'm gonna test out by creating just a simple square grid and try to complete the setup first for the distortion. Then when the setup is done, I could try with other types of grid geometries like hexagonal grid, triangle grid, Voronoi or something, which could be more on top of a three-dimensional geometry. Okay, but it's easier to do on top of a 2D geometry first, so let's do that. Alright, so I first going to create a geometry node, then create the grid node like this. So first thing I would like to decide is how many rows and columns, in this case how many cells you want to have in this grid, as well as the size. So let's create some null node to have all the parameters that I want to control later on for ease. So I am going to first of all create a null node, name this controller to have all the parameters that I want. I'm gonna color this to blue. Okay, open up the parameter interface, and the first value that I would like to have as a parameter is the size of this grid. So float, gonna name this size, let's say from 0 to 10. Also, I would like to set the resolutions for the grid, which is going to be related to the number of cells. So let's do that. I'm gonna name this resolution from 0 to 100, or maybe 1000. That might be too much. Well, let's go 1000 for maximum. Okay, so for the size, I'm gonna set it to 10. For the resolutions, I'm gonna set it to 100 for now. Copy the parameter and set the size to X size and Y size of the grid. And then for the resolutions, I'm going to set it to the number of rows and columns. All right. Okay, that looks good. Now, I am just going to use this grid as a first test in order to create the distortion, so that you will see the final output quickly. So in order to do that, you could just move this grid itself, but what I would prefer is to have line drawing distorted, which would look more prettier for me. So I am going to convert this into a bunch of lines for these edges. So I'm going to use the convert line node to convert the grid into a bunch of lines like that. And what I'm going to do is to move each point position of this grid network using some kind of attractor points. All right, so let's do that. First thing I would like to do is to test with a single point how are we going to move the grid, so that we'll be able to understand better what we're going to do. So in order to do that, I'm going to create single point using add node for testing, and let's move the point position to somewhere you want to use it as attracting points, attracting position, maybe somewhere around here, like that. All right, and another thing you want to set is the radius, how much strength this point have, like the magnetic force. So what I'm gonna set is a radius to determine the affection, like distance from this point position, as an attribute to this point. So I'm going to create a create attribute node, attribute create node, and set an attribute called radius. Just gonna call rad as a float value. And let's say, so the size of the grid is 10, so maybe set the radius to 3 for now. This is just a test. Okay, and I'm going to try to use this point as an attractor point and try to try to create distortion to this grid together with this attractor point using a point wrangle. Okay, connecting the grid to the first input and connecting the attractor points to the second input. I'm gonna name this single point distortion. Right, so let's try to do this. So this will be the base for our final setup, and it's not that hard to do, I think. So first of all, what I would like to do is to get the point position of this attractor point inside this wrangle. So let's do that by using a point function from the second input called get that p attribute, which is the point position, and there's only one point, so you can just say 0, which is going to be the first point. Right. Now, what I want to do next is to calculate the distance from each of the point on top of the grid to this attractor point, okay, which is somewhere around here. So what I'm going to do is to calculate distance from this point to this point, this point to this point, and so on for each point. And if the distance is within the radius of this point, then we're going to do this distortion function or distortion movement based on the vector between this point and all the other points. So first let's calculate the distance. Distance is between the current point position and the attractor point position. Okay, and let's also get the radius from the attractor points, which is point from the second input. We have the radius attribute created, which is this one. Okay, and what we're going to do is to calculate or determine if the distance is within the range. And what I'm going to do is to just clamp the value. If the distance is more than radius, then we're going to clamp this distance to the radius by using a clamp value or you could also use maximum or minimum. Yeah, minimum between the radius and the distance. So in this case, if the distance is more than the radius, then the distance will become the value of the radius. If the distance is less than radius, then distance value will not change. Right? So meaning that the distance will be clamped at the radius. So the value should be in between 0 to the radius. Okay, for this one. Now what we want to do is to convert this distance value to the force value to move the point for distortion. So for ease, it's always better to normalize the value when you want to remap the value from one value to another. And in this case, the value right now is in between 0 to radius, and when you want to normalize it, you want to convert it in between 0 to 1 first. So for that purpose, you can just divide the distance by radius in this case, because the maximum value of distance is radius and it's in between 0 to radius. So if you divide it by the radius, which is the maximum value, then you'll get the value in between 0 to 1. Right, now the distance is in between 0 to 1, or maybe I could create another variable so that it's easy to understand. So let's create a value called d and calculate the division between distance and radius, and the d is in between 0 to 1 right now. Now that we have the value in between 0 to 1, we are ready to convert this into some force value in order to move the points or in order to distort the point. So let's decide what kind of value we want. Now let's think about how we want to move this point. I'm going to try to draw some basic sketch here. So we have a bunch of grid, and what we want to do is to move each of these points to some direction, and that direction is determined by this attractor points, which lies on top of the grid right now. Okay. And currently we have calculated the distance between each of the point. Okay. And let's say this is the radius. And if the point is within the radius, meaning if the point is within this circle, then we want to move these points, which is within the radius. And the direction, first of all, the direction we want to move is determined from this attractor point to this each point. So meaning for this point, we want to move to this direction. For this point, we want to move from this attractor point to this point, so this direction, and so on. So we can determine the direction. What we want to do now is to determine how much you want to move for each point. And that can be determined by the distance itself. So if we should decide how we going to remap this distance value for the movement value. So if the point is close to the edge of the circle, like somewhere around here, the distance is pretty close to the radius. In those cases, maybe we don't want to move those points that much because it's far from the attractor points. But if the point is close to the attractor points, which is close to 0 in terms of the distance, we want to move this point a bit farther than the one that's on the edge of the circle. So meaning that if the distance is larger, then we want to move less. If the distance is smaller, then we want to move a lot. So that's what we want to do in order to remap this d value, which is in between 0 to 1 right now. So if the value is close to 0, which means if the value is smaller, we want to move further. If the value is close to 1, meaning if the value is close to the radius, then we don't really want to move that much. Considering that, we can use the fit function like fit01 for this d to move the point, such as if the point is close to 0, maybe we want to move the point to the value equal to 10. If the d is close to 1, then we don't really want to move. This is just a temporal value. Let's just test how it looks like with this. Okay, now that we have a value d, which is going to be used as the moving distance, we are ready to create the direction. And the direction is pretty simple to determine. It's just a current point position minus attractive points normalized, which is the vector that I have drawn on the sketch. Okay, so combining this direction together with this distance, you'll be able to create the force value by multiplying two values together, and we are ready to move the current point position using this force. And let's see how it goes. Okay, so maybe we moved a little bit too far, as you can see. So let's control this value, maybe using some parameter value like move. Okay, so if we move this slider value, you can see that the scale starts to happen, the grid starts to distort based on the point position on the center, like that. And it's moving linearly on top of the plane, like this. Now this looks okay. Maybe let's increase the range from 0 to 10 and see what happens. Okay, so this looks like this. Now this this is okay in terms of the distortion, but it's a bit, you could see these edges a bit too far. I mean, it's not really like a smooth edge right now, as you can see right this. And on the center, it's a bit too, it's moving a bit too much, okay, as you can see. So I would like to tweak this a little bit more so that the movement will be a bit smoother and not too much on the center, a bit smoother connections on the edge and so on. So in order to do that, there are I think there are a bunch of ways to do this. One way is to use something like a power function or logarithmic functions. Other way, you could manually control the how the distance affects the remapping by inserting some ramp parameters in between this and this. So this is where we have created the variable d, which is in between 0 to 1. And since the value is in between 0 to 1, we could use a ramp parameter to control how the value will change based on the user drawn curve. I'm gonna name the ramp and create a ramp parameter like this and promote by clicking this button. Then you'll get this linear graph, and by changing this graph value, you'll be able to control how it affects, how the remapping affects. By using the d value on the x value, you get the value the output value from the y-axis. So right now the curve is linear, so when you input 0.2 as an input, then you get 0.2 as an output. But if you make it like a curve graph, like converting this to a B-spline on the both ends and add some points like this, you see that when you input the 0.2 on x-axis, you get something less than 0.1, 0.05, somewhere around 0.05 for it as an output. Okay, and you get different result like this. So by controlling this curve, you'll be able to create more smoother and better result looking functions. Okay, so this looks a bit more smoother in my case. I think having a smaller looks like a sine wave, but looking better. Okay, somewhere around here. How's this? Now I still have some problem on the center, so maybe I do need to control how it affects on the center point positions as well. Let's see if I can do how I can do that. If it's close to the center, maybe I can increase this is doing something. So in this case, if the distance is close to 0, we are converted into 1 in this case. So meaning, and later on we are going to remap flipping this value so that if the value is equal to 1, then the scale will be close to 0. So in the center we are not getting any forces, but then when it gets a bit far from the center, then we are starting to have some forces like this. So this might work, might not work, I'm not sure. Well, I am going to just keep this as this sine wave like functions, and try to change this move value a little bit and see what else we could do. Okay. All right. So, and one thing you could also try is to move the point on Y direction as well. Currently the point is on top of the grid, like on X, Z plane, like that. But if you move it to the Y direction, you start to have a three-dimensional distortion, like that. And that way you see more better result on those too closed on the center point position of those grids. Okay, so that's one thing you should consider, I guess. Now, but I'm going to keep trying it on the Y equal to 0 for now, for testing. Okay, so this is how it looks. And let's see what else we need to do. Okay, one thing you could do, one thing you could try next as a next tryout is to try to use multiple point positions instead of just one. Okay, so right now I have just I just have one single points. Maybe if you add another one customly, currently only one point is being used, like this, which is not that interesting. So let's try to think how we can use multiple points together to affect to each other. Okay, so going back to the point wrangle, and let's see how we do that. So right now, when we are getting the attractive points, we are just using this 0 as a point index. And since you are just using 0, you're just getting the single point positions. So in order to do this for multiple points, you do need to create the loop to look all the point positions from the second input. So in this case, we're going to create the for loop, and we're going to count up how many points we have from the second input, like this. And then the I will be the index of the point, so we're going to replace this with I, and this one as well, I. And now you have now created 2 points being used together to create an attractor combined together. Just like that, pretty easy, isn't it? So if you have multiple points, you could still do that. Like this. Okay. That's that easy. Now, one thing I don't really like about this is, again, this center point position is moving a bit too far. So that's what I want to fix. Yeah. So let's see how I could fix this. First thing is by just moving this move value so that we don't move those center point that much, and then we can move this a little bit. Well, though I still want to use the radius. Let me try to increase the radius and see how it works. If I set it to 6. So in this case, if the point is close to 0, then you'll have wait a minute. Is this correct? I might need to use this. No. I think it's okay. Okay, well, what if I set to this value to 0, this set to 1, and this one to... Okay, it's a bit hard to control, isn't it? Yes, I might just need to move the point a little bit underneath or upper direction for a better smooth result like this. And then if you want to have this as a 2D pattern, then you can have additional point wrangle. Then just flatten this by projecting the y value to 0. And this will become 2D. Maybe this is much better. Okay, so maybe controlling the height direction. The height of the point is also important in this case. So let's have that as a reminder as well. Okay, so now that we have a system to use a multiple point position to be able to control the grid or distort the point, distort the grid. Let's see what else we could do. All right, so now we have this one. Might want to have a little bit of might want to exaggerate the edge a little bit more. Maybe the radius a bit too much. Yeah, that looks better. Okay, looks interesting more. All right. Okay, now the next thing I'd like to do is to try to have multiple points moving like an animation, and also having like random radius might also be interesting. Right now every point have different, or has the same radius created by this create attribute, but instead let's use some vex to create a random value and also move these points randomly on top of the grid. And maybe moreover, maybe you could create a loop animation using some periodic noise value to make it interesting as well. So instead of using these points, let's create the switch. If you want to make it as an automatic point, I'm first going to create a bunch of random points on top of the grid by creating a scatter node. Let's create a new node in between the grid and the convert line. Let's call this grid. And then from this grid, I'm going to create a bunch of points, maybe without the relaxing. And this will be the attractor points to used with this distortion. So let's try, instead of using the add node, what happens if you just connect this point, and this is what I get. And that looks a bit too noisy. That is because we are having too much point position, too much points. All right, well, that is too much. That looks too much. I guess that is because we have a bunch of points with a bunch of radiuses. Maybe we do need to, when we have a multiple point position, maybe we need to deal with some kind of multiplication later on in order to in order to get the better result. Comparing with this point and just 3 points, you could easily see the differences. Maybe, let me just set everything to 0. Well, I guess it's pretty close, I guess. Just the difference with the number of points. Yeah. Okay. So, let me I think I should change something in order to make this distort, not to distort that much. And where that should be, maybe instead of using fit 01, I could try to say 0.01 to 1.0. Nope. 0.8. Nope. Not really working, is it? Okay, well, forget about it. I'm just gonna move the Y direction. Alright, so where was I? So I wanted to create this point moving randomly and also set the radius randomly. So let's do that using another point wrangle. Okay, and first of all, I'm going to set the radius randomly. Okay, so that should be easy. I'm just going to use the random function based on the point position. If you want, you could add additional seed value as well. And since this is in between 0 to 1, let's use the fit 0,1 functions to make the value in between minimum radius to maximum radius of your choice. So min radius and maximum radius. Okay, seed could be any value. The minimum radius and maximum radius could also be any value. Let's have that as a value in between 0 to 10. And also let's also copy these value to this controller so that we can control this later on from this controller. Okay, so we have a seed, minimum radius, and maximum radius. I'm gonna just make everything lowercase, just having some spaces. Alright, now let's try to use this, switching to these noise points, the random points. Oops, that looks a bit too much. Let's see why. The minimum is in between 0, the radius in between 0. Okay, we haven't set the radius yet, so the radius is this. Okay. So controlling the maximum radius, you see some kind of distortion is happening like this. Right? And if we change the seed, we could also see that some kind of radius changes is happening as well. Maybe we could also use this seed for the scatter node global seed, so that we could also change the point position based on this seed value. Alright, now let's also move this point randomly and also move this point to the a little bit to the y direction, either on upper direction or down direction, the bottom direction. So first thing first, I'm going to create a point wrangle node again and move using some noise function. Oops. First thing I would like to do is to decide the height of these points. Okay, so and that could also be random, I guess. So let's do that first. I'm going to create the height value, or yeah, height value, and based on the randomness, we could change the y value randomly throughout the moving, but in my case I'm just gonna fix the height and only moves the x and z value, but it's your choice. You could also move this height value as well if you want. In my case, I'm just going to try to create the random height value using additional seed and additional value. I'm going to copy this seed value. And this will create the value in between 0 to 1 again. Now, I want to remap this again to your remapping choice, or your target choice. In this case, minimum height and minimum or maximum height of the random. So let's say minimum and maximum. Let's have that as a parameter as well. Minimum height goes here, maximum height goes here. Minimum age from 0 to 10. Maximum age 0 to 10. Alright. And use this for a y coordinate of these point position. Okay. Now the point has been moved to somewhere really far from the grid and it's not really affecting the grid anymore. So maybe we should make this height a little bit smaller. Like that. And it's creating like a crate. So if we want to create a more like a bubbly shape, maybe we should make these value negative. So let's also create the range from the negative. So in between negative 10 to positive 10. And see what happens. So the minimum, I'm gonna set the minimum value to negative. And if when the positive value, the maximum value is positive, then you get this kind of a landscape of the distortion, which is still interesting. Okay, but at some point you get these ugly distortion as well. So in order to prevent that, maybe having those two values both to negative might make sense. like that. Looking good. Okay, and if we increase the radius, we see more affections to each other. Alright, getting better. And let's go back to the point distortion. Now it's not really a single point distortion anymore, so I'm just going to rename this to point distortion. And if we change some parameters like the moving scale value, and this becomes more interesting. So let's have this value to the parameter as well. Okay, copying this moving value, or maybe we should name this to distort. Alright, from 0 to probably 1. Okay. And play around with those parameters. Interesting. Getting good, getting better. Alright. Okay. So this looks pretty nice. Ooh, this is a bit ugly. Let's try to fix this later. I don't really like how it looks when you have negative and positive at the same time. Okay, so it's time to try to move the point so that we could see some interesting animation. Okay, so as soon as I have set the height, it's time to move the x coordinate and z coordinate based on some noise value. And the reason why I'm going to use the noise is because it can be used to create some random walk animation based on the frame value. And by using a function called pnoise, you could create a repeatable noise value which can be used to create the loop animation. So let's do that. So I'm going to create the moving direction first of all using some pnoise function based on the current point position of the point, multiplying by some noise smoothness. Which might not really be useful, but in this case maybe we want to have a really large value for each point to move in different directions. If the noise smooth value is smaller, then the point position is too close to each other, creating a similar moving direction. Okay, now, and what else I need? So in order to also animate the value, we also need to use some frame-based value. Okay, so I'm going to, since this is a vector value, I'm going to use this frame as a vector value by creating a 0 frame 0. So in this case, I'm using a frame value to a 0 to the y axis, right? And since I want to create a repeatable animation based on maybe from the first frame to the end frame of this setup or this project, I'm going to first normalize this frame value by dividing by the frame end, which is 240 in this case. So you get 0 to 1 for this value. and then multiply by some integer value, like how many, which is going to be used for the parameter for this periodic noise. Okay, so I'm going to name this as a py starting from 3, and then multiply py to this one. Now p noise should use 3 additional parameters in order to create the periodic noise, which is x periodic numbers and y periodic numbers and z periodic numbers. For x and z, you can just use any value. Might make sense to give a high value, but these values don't really need to be repeated, so you can just give a high value. For a y value, you could make it parameterized like this one. If you have a less value, you get really small periodic noise. Well, I'm just gonna show you how it looks by changing these values. Okay, so let's promote the noise smoothness. Give it a high value like 100, should be okay. Now that I have a velocity, let's have this as a parameter as well as an integer. Period. Starting with 3. Now this, by using p noise to create the vector value, you also get the y value, which you don't really need. So in this case, so I'm going to set the y value to 0, and also x and y in this case have a positive value in between 0 to 1, so I want to make it also going to the negative direction. So I'm going to subtract x and z by 0.5 as well. Right, now we are having the value in between minus 0.5 to 0.5 for both x and z, and 0 to y. It's time to multiply this velocity by how much you really want to move this point maximum. So I'm going to multiply by some float value, which tells how much the point should move. And in this case, I'm going to try to set as 10 for now. Now I am ready to move the point using this velocity and see how it goes. So if I play it, I'm just gonna look at the point, and if I play it, now the point is randomly walking around the space using 10 as maximum distance. 3 could be called as a speed. If you set it to 1, you have just 1 periodic noise throughout this from first frame to end frame, and if you have 3, you have 3 periods within this first frame to the end frame. So if you have higher value, the speed gets faster. So you could also call this as a speed. Maybe I like 3 as a value in this case. And the noise smoothness doesn't really mean much. It's just to make every points moving in a different direction. If the value is small, then all the points, it's trying to go to the same directions, like this, which could be interesting as a like a swarm effect, but not too much for this one. So I'm gonna make it high enough so that every point moves randomly. Okay, as a result, using this as a attractor point for this grid, you see something like this. Yeah. and adding some flatten function. In this case, just setting the y value to 0. You can get a 2D geometry like this. Right? So this is the complete basic setup in order to create grid distortion. Okay, which doesn't look that bad, isn't it? Okay, and going back to the 3D, trying to change those parameters that I have set, like the maximum radius, minimum radius, maximum height, minimum height. Interesting. Distortion, and so on. Now, it looks okay, but this is the situation that I really don't like right now. So this is what I want to fix next. When we have the minimum height and maximum height going to the opposite direction, I don't really want to have something like this really ugly like distortion. So let's see how we could fix this. I think it's due to some functions that I have wrote inside this point distortion. So let me see how I can fix this. Okay, so looking from the start. Okay, so each time I calculate the forces, I'm adding to the point position. Instead of doing that, I'm gonna try to create a total force value outside a for loop, and try to add this, try to move the point after leaving this for loop like this. Okay, and what we want to do is to try to calculate the total force inside this for loop, meaning we're going to add this force inside a for loop, and suddenly, I don't know really why, but the result looks much better. How is that? I think it's simply doing the same thing, but due to some Beck's, I don't know, calculation order, something different result is happening. So, well, anyway, the result looks much better in this way. So that's some tips you might want to know, you might want to be remembered. Okay, so this looks much better. So if I set the minimum height 0, maximum height 0, and maybe the distortion smaller, you do still see some ugly things, but not too much than the last time. That's good. That's good. Let me still test what I could do. I'm gonna looking back to what I have created previously and see what's the difference, because the one that I have done previously looks better. When it is equal to 0, I still don't see these ugly distortions. So I also want to fix this one. Let's see how. Okay, this is not too good, is it? Right. So one thing I am missing, let's see, is Let's see what I am missing here. Is not really sure. Not really sure. Probably these curve. Trying to change the curve. Nope, not really. Not so much. What else? If I change the radius to something like this, no. Okay. Let me try to think what's causing this problem. I mean, I could see why, but because if the distance is close to 0 for the attractors, we're getting this kind of a strong distortion. Although I think there are ways we could deal with this thing. Okay, first of all, let me try to move this one, which is currently called move right here, outside the loop. Like this. Okay, and if anybody has some advice, I'm happy to hear it as well. Okay, and we are checking all the point positions. That's okay. We're getting the point position of the attractor. That's also fine. Calculating the distance, right? Getting the radius. That's also good. Now, how about this? How about this? Is there any chance that we get a value less than 0? I don't think so. I mean, this is pretty much the same by using the clamp for a distance which is in between 0 to radius. So yeah, getting the same result. And we are dividing the distance by radius so that the value will be in between 0 to 1, using the ramp parameter to remap this value, then remapping from from move value to 0. That's also fine. And also wait a minute. Is this okay? Okay. So last time we had point position inside here. The problem was this point position has been like modified for the next iterations. That was a problem. So that's the reason why it works outside a loop better. Anyway. So let me try to copy this current point position like this, and instead of using add p, let's try to use pos, but still doing nothing. Yeah. Okay, I get why. The reason why I don't really see a better result when the point is close to the attractive is because I'm normalizing the direction. That's why. I should, instead of using the normalize, just divide this vector by the radius so that the value of the vector is in between 0 to 1 in this case. Okay, now much better. Alright, this looks much better. More smooth, not too ugly distortions happening, and still works positive, negative, and I might need to increase the range of this distortion. Alright, like it. Okay, getting better, isn't it? Alright, looks good. Now, one little problem is that the height of this distortion might be regularized. I mean, meaning gets a bit too low right now, as you can see here. That is because I have divided by this radius, which also causes the height to be smaller. So maybe in terms of the distortion on X and Z direction may be okay in this case, but maybe I also want to control the Y direction scale as well. Yeah. So let's have additional parameter to control the Y scale, shall we? In this case, I can just get the Y coordinate and multiply by some additional multiplier. So if it's 0, it's flattened. If it's going more than 1, you get more height distortion. How's that? Yeah, I think I like it. Okay, so let's have that as an additional parameter. So I'm gonna name this to XZ distort, and this additional distortion value to Y distort. And set the radius, set the range from 0 to 10. Like that. All right. Getting better. Okay. Now everything looks good. I think. Let's also copy these parameters as well to the controller. Noise smooth. Let's have this somewhere around here. Period. Move max. Let's organize these parameters a little bit. Having separators. Okay, so this will be seed. This will be noise smoothness. Should be high value, so I'm gonna set from 0 to 10 the period. This is the noise period. which could also mean noise speed. Zero to 10 is fine. Noise move distance, just gonna say noise move from 0 to 100. That's pretty much it, I guess. Minimum radius, resolution size. Okay, so I think every parameter has been set. Maybe I can also have this number of attractors as a parameter, additional parameter. So going back to here, maximum to 1000. Link this. All right. More points you have, more movements you get. Like that. Yep. Getting interesting. Wait. All right. Okay. Looking better. Looking good. Let me save this to so that I don't lose the process. Okay. Now, I think in terms of the setup, this is pretty much done. You could now test out with different kinds of grid, such as like hexagonal grid, Voronoi grid, and still should work in the same way. For example, if I create additional another grid here, in this case I'm going to set, let's see, let's try to convert this grid into a hexagonal grid or a triangle grid. Now in order to convert this into triangle grid, I am going to use the divide node. Now this itself is triangle grid, but the size of the triangle is different on these each edges. So we, in order to make each edge length the same, we need to scale this in one direction. In this case, we need to scale in this direction with some kind of value. So in order to easily do that, first I'm going to rotate this 45 degrees in y-axis like that. Then you can see that it's using some kind of value in x direction, we should be able to scale it. So let's see how much we need to scale. Okay, right now we have A, and we have this one is, this is 2a square root of 2a or square root 2 multiplied by a. Okay, and we need to scale this with some values to make each triangle edge shares the same length. B. Now this b value, that value doesn't really change, so this is equal to square root 2a. So this b value should be convert it into this square root 2 by having some scaling. So the scaling goes from this length to this length, which in this case let's call this L1, this calls L2. I shouldn't write here. I shouldn't write it here. L1, L2. So the scale value is L2 divided by L1. So this is the value we want to calculate. Okay. And in order to have that, we know how to calculate L1, which is, in this case, we can use some trigonometry. So this is a cosine 45 degrees. Since this is 45 degrees, this is L1. Is it? No, it's not. Why it's... No, is it? No. That is... What? Oh, wait, that is sine. I mean, it's the same as cosine in this case for 45. So either way it's fine. So L1 is a sine 45 degrees, and L2 in this case, we don't know. We don't. Do we know? Yeah, we do know. We have this value here. So L2 is can be calculated by let's see. So B is also this value, so A multiplied by sine 60 degrees. Okay. So this is L2. Now we have the multiplication to A multiplied by sine 60 degrees divided by A sine 45 degrees, and we are getting rid of this A value, so we are getting sine 45 degrees to sine 60 degrees. So this should be the scale value, hopefully, if I'm not mistaken. Okay, let's remember this. So we want to scale it in this case, this direction, which is Z direction. So let's try adding another transform node. Scale. So square root 2 multiplied by sine of 60 divided by sine 45. And looks like we are getting the right triangle. Hopefully, let's check it. Convert into the lines will give you a line length for each lines. So let's check if we are getting the same length for each edges. Yep, pretty much the same, just 0.00002 difference. So I think we can say it's the same length. All right. Now we are getting this kind of diagonal scaled value, which is still okay. If you just want to distort this, looks interesting. But you could still trim it out, trim it to the original shape, original like grid shape if you want, by rotating back 45 degrees, then just trim it using some boolean between surface and surface as an intersection. And for the second input, just use this grid. And you should get the these. Oops. I should instead use the one that doesn't have a grid inside. Okay, so you can just trim the square like this as well. So this is a triangle grid in a square shape. Let's have a switch node so that we can switch between those different grid. Like that. So this is a result of the square. This is a result of the triangle. And creating a hexagonal grid is pretty easy from this triangle shape. We just need to use the additional divide node and calculate the dual mesh. Checking this one, and you instantly get this hexagonal grid. Now edge is a bit too dirty, so if you don't want that, you could do this before trimming, somewhere around here. Then do the additional boolean retrim like that, which should at least create a better edges, not on the corner, but good enough. Connect this to the switch to the hexagonal grid. All right. Looking good. For Voronoi, you know how you can do it, so I'm just gonna skip it. Now, a bit challenging things to do is to use this on three-dimensional surface. Okay, if anybody is interested in this, converting this 2D functions to a 3D, let me know. If not, I could just end this right here, since we are doing this for 1.5 hours. If you could wait until additional 30 minutes, I could try to convert this into a three-dimensional, more generalized way to use it for 3D surface or 2D or 3D. Okay, let me know. Okay, so thanks for the comment. Some people are interested, so let me try to do this. I'm gonna try to use the simple geometry for testing. Maybe just use the pig head or rubber toy, anything. Maybe pig head. Let's make this scaled up. Maybe we could also control the scale of this pig head using this same size parameter. Right? Okay, now first thing I would like to do is to create a three-dimensional grid, which is just these edges. Okay, you could use the original edge network from the mesh, or maybe you could use something like remesh to create your own grid. Let's try to do that. I'm gonna remesh it. Maybe somewhere around here. To make this a bit more interesting, I'm gonna create the compute dual mesh. Create a dual mesh using another divide node. Compute dual looks better. All right. Now connect this to this switch, having this geometry output from the switch node to to the grid, convert it into the lines like that. Let's first see what's going to happen with current setup. As you can see, the noise is moving on, how do I say, the XZ direction, so it's not really moving the way I want, and also the distortion is only happening also in XZ direction, so something looks really weird, not really working as I want it to be, so we need to fix that. The things that I need to fix is just the coordinate directions, make it more generalized. Instead of using Y or X or Z, maybe we should use like a normal direction. So let's see what's happening here. First of all, we have scatter node. Where is that? Do we see it? I don't really see anything. Let me delete all those unnecessary attributes like color, texture, or something like UV, or something like that. So I don't really need a UV. I don't really need the material. Oops, getting error. Okay, let me try to salvage this. Okay, should be inside a temporal folder. Now this should be it. Damn. Okay, so this is the crashed file. I'm gonna copy into the desktop and open this up. Okay, sorry for that. This happens really often. Alright, where was I? Okay. Why am I having the shop material on some point? Is that correct? Let me check. I still see... Okay, looks better. Now, so I have points, I have random radius. This, from here, this is, until here, this is okay. This should be okay. Because it's not really related to the coordinate or axis. Now this one should be fixed. Right now, this is fitted inside the Y close to 0, which is creating some weird movement. We actually want to move these points on top of this geometry, just like the points were moving on top of the grid. So we need to fix this one. Okay, now it might be a good idea to keep this one for your reference, for your later reference. So I'm gonna keep this as a 2D setup and try to create another one as a 3D. I'm just gonna duplicate this and call this 3D, which could still work on 2D as well, to make it a bit more generalized one. Okay, so going back to the move noise, let's see where we need to fix. So first we have created this height value, which is okay, which is still okay. This is the problem. This is where we need to fix. We don't really want to fix the height value at the y value, but instead we want to convert this based on the normal direction and the current point position. So to do that, I am going to first of all calculate the normal of the input geometry, maybe for each point, like that. Now by doing this, you'll be able to attach a normal direction to each of the scattered point, like that. Alright, which is useful. Now going back to the move noise, what I could do here is to first of all, from the current point position, add the height to the normal direction, like this. Now the point has been moved based on the current position of the surface, either on negative direction to the positive direction. I think in the current parameter we have from minimum height, maximum height, both negative, so all the point should be inside the surface, but seems like not yet. That is because we are having additional moving points. So let's disable this for now, and let's check that all the point is inside the surface, inside the input geometry, and yeah, it is right now. And by controlling these value, minimum height and maximum height, if I set this positive, some of the points go outside, and if both minimum and maximum height goes positive, then every point goes outside. So that's good. Okay, let's keep this both negative so that all the points is going to be inside the geometry for now. Alright, now that is good. Next thing we want to do is to move this point on top of the surface. Yeah, on top of the surface. So to do that, there is many ways we could think of. If we want to keep these points moving inside the surface, then we do need to think about if we want to keep the distance from the surface to the points to h, then we do need to think about the projection. Maybe that makes sense. Yeah, but if we have a complex geometry, then at some point just might go outside the geometry, so maybe we don't really need to think that strict. Let's just think that the point moves to the tangent vector of this surface, where the point has been projected to the surface, and we get the tangent vector on that surface, and just move it based on this tangent vector, considering that the projected point on top of the surface has this temporal construct plane, and on this construct plane we have x-axis and y-axis, the virtual x-axis and virtual y-axis, and we want to move this point to this virtual x and virtual y. I don't know if that makes sense. I'm gonna try to draw the sketch. What I meant is that when we have a virtual surface, I mean the 3D surface, and there's a point, and we need to think about in which direction we want to move the point. using the random noise. Now, my method here is to first of all try to project this point on top of the surface, and by doing that you'll be able to get the tangent vector on this surface. Okay, and use one of the tangent vector. I mean, on top of the surface there are many tangent vectors available. Just choose one of the tangent vectors as x-axis. Okay, and rotate this tangent vector 90 degrees on top of this surface using normal direction as an axis. 90 degrees, you get y-axis. And based on this x and y-axis, I want to move this point along this plane. So in this case, this direction. So make using this as a virtual xz plane like we were doing on the 2D. That's what we want to do for each point. So each point has different plane, right? That's what I meant here. So first thing first, we need to create these axis value for each point. And to do that, let's see where we could do. Now, for this one, which is creating a periodic noise, it is using frame for just y value, but since we are on 3D, maybe we can just use this value for y-axis into the normal direction on the axis. So to do that, what I want to do here is to change this to normal direction multiplied by frame divided by frame end and multiplied by period. Okay, so this is a bit tricky because we only have x, y, and z. So in order to estimate the integer value for x, y, and z, wow, that's pretty hard. It's pretty hard, isn't it? Well, we can just say everything is py. This should still work, I guess. Let me see how it try to move. Yeah, I guess not that bad. Although it's not creating a periodic, it's not repeating itself, isn't it? Nope. Not really. That is because, yeah, this value. Okay, this is more trickier than I thought. Right. Okay, well, wait, let me think. When it was set 0 like this, instead of normal, we were able to create a repeatable. That is because this value is in between 0 to py, and this was working because of this value. So this integer value is the the maximum value of this y value. So when I am going to use the normal multiplied by py, normal multiplied by frame divided by f and multiplied py, in order for this one to work, the y coordinate of this normal multiplication should be, the maximum should be equal to 3. Yeah, this is pretty tricky and doesn't really work well. So instead I am just going to use frame multiplied by this value for every x, y, z coordinate. Like this, which should create a repeating, yeah, noise, which I don't really like how I wrote. So let's make it as a variable. Just gonna copy this one. Use x, y, z for everything. Yeah, and maybe I don't really like the name xpy after all, so let's name this ph instead, because we are not using any axis right now. Okay, so it's okay. Now we are okay with this p noise value. It's time to create a direction in which direction we want to move. Previously we were moving to the x and z direction and not moving on y direction, but currently we are having the different situations. We don't want to move on the normal direction, but we want to move on the tangent direction. So in order to create this tangent directional vector value, we do need to have a x and y axis first be created. So in order to do that, first of all, we need to get the projected, we need to project the point to the surface and get the tangent vector. And in order to get the tangent vector, first we could get the normal direction on that surface, right? Which is, I think it's equal to the current normal direction, so maybe we don't really need to think about the projections after all, do we? Let me think if we need to yeah, I think we still need to project the points to the surface in order to get the estimate the tangent vector. Now to do that, in order to estimate the tangent vector, what we're going to do is to first of all project or get the nearest point position to this point, to the surface. It's a bit hard to see. Let's look at this point. Now probably the closest point position from this point to the surface is somewhere around here. Okay, and what I'm gonna do is to get one of the edge as a tangent vector, which is not perpendicular to the normal direction, so we are going to use the cross functions to make it perpendicular to the normal, meaning we're gonna fix this direction so that it's going to be the tangent vector, then rotate it 90 degrees using normal direction as a axis. So first I'm going to get the nearest point position from the surface, and to do that we need to have this as a connected to the second input as a guide. So from the second input we are searching for the closest point position, and then from this new point, what I want to get is the neighbor point. Any neighbor point is fine. For this point, this point, or this point, or this point could be fine. So I'll just get the first neighbor point using a neighbor function for the second input for the near point and get the first neighbors. Okay, now that I have 2 points, it's time to calculate the direction from this point to this point. To do that, we need to get the positions. So get the point attribute, the position attribute, both for the new point and the neighbor point. And calculate the subtraction of this vector to calculate the tangent vector. And normalize this. Now this itself is still not a tangent vector, which is not really perpendicular to the normal, so let's fix this by using a cross function, a cross product, which will create a perpendicular direction between the normal and the tangent, and as a result you'll get, so let me explain what it means. Let's see, it's a bit hard to see, so let's see, we are looking at this point on top of the surface, okay, and the blue line right now is the normal direction. Right now I have just got this direction inside, which is the calculated from this point to the neighbor point. Okay, now it looks perpendicular to the normal, but it's not strictly not. In order to calculate the strict perpendicular direction, which is going to be the tangent vector, you can calculate the cross product between this vector and this vector, which will give you a direction somewhere to this direction, which is perpendicular to both normal and this vector. And now this vector is both perpendicular to the normal and this neighbor vector. You could use this as one of the tangent vector. Then as soon as you get it, you can just rotate this 90 degrees using this normal direction as an axis to have another axis, which is going to be used as the y-axis, virtual y-axis. And the first one will be virtual x-axis. So what was I have created, let's just name this x-axis equal to the cross product between the normal and tangent. And when you use cross product, which has different size, which might have different size, it's always better to normalize. Now let's also create the y-axis, which is just rotating the x-axis by 90 degrees. So let's create the rotational matrix, rotating the matrix by 90 degrees using normal direction as an axis. Then multiply x-axis by matrix. Is this correct? So matrix, angle, axis, yeah, this is correct. So now I have x-axis and y-axis. I should be able to have. Now, as soon as I did it, it's time to use these axes to define in which direction the point should move using this p-noise, which is currently in between 0 to 1 for both x, y, and z. Maybe it's better to subtract this vector value by every coordinate by 0.5 for ease, and multiply by 2 so that the value is in between -1 to 1 for every x, y, and z. Okay. Now it's time to actually create the moving velocity. Somehow we don't really. So in order to do that, what we want to do is to project this this random vector velocity to an x-axis and y-axis, and get the value, the length of the projected x-axis and length of the y-axis, and add it together. I'm not sure if that makes sense. So when we have, this is really a vector calculation, which a bit hard to understand, but when we have these x, y, and z axis, and we have this random velocity on 3D, currently having x, y, and z, or let's call this A, B, C, and we have this virtual plane, which looks like this on top of the three-dimensional space. This has this virtual x-axis and virtual y-axis. Okay. And what we want to do is to project this velocity on top of this plane to create the vector which runs on top of this plane. And in order to do that, the easiest way is to first of all project this velocity to y-axis and get the distance of y. Why am I having black color? Yeah. Calculating the projected y distance. And also project this velocity to x-axis as well, and getting the projected x distance. Okay. I'm going to call this xd and yd. So in order to get the final velocity, let's call this v. What we need to do is to just multiply the normalized x-axis vector multiplied by xd, which is the projected x distance, plus y-axis vector multiplied by yd, which is the distance projected to dy, the velocity projected to the y, and the distance. So the question is, how do we calculate this projected distance? And that is pretty easy to do. You just need to use a dot product between the velocity and y-axis or x-axis. And either one of the dot product should be normalized in order to get the projected lengths. So one of the dot product could be velocity, and one of the dot product could be a normalized x velocity, and as a result you'll be able to get the projected x distance. Yeah, and that's how you create this projected velocity value. Sounds a bit complex, but if you imagine it in 3D, I think it's easy to understand. You just need to know what dot product do for 3D space for vectors, and that's pretty much it. So where was I? So I have x-axis and y-axis. Now we need to calculate the projected xt axis, projected x distance, and projected y distance. So float xt is equal to a dot product between the current velocity, which is this one, and x-axis. Float y distance is dot product between velocity and y-axis. Both x-axis and y-axis has been normalized, so we don't really need to worry about it. Now that we have these distance, we can recreate the velocity. I'm gonna just rename the velocity to final velocity by multiplying the x-axis multiplied by xd plus y-axis multiplied by yd. And since it's being projected on the plane, dy is already equal to 0 when we were at 2D, and just doing the same things as this ones do. So just delete, and finally multiply with some moving maximum value and add it to the point to move. Okay, and hopefully this will do what we really want to see. I think we are moving a bit too far, so let's give the move max to 3 and see how it moves. And it's a bit hard to see. Let's check it by copying the sphere to the point, see the movement more clearly. Doesn't really need to be that strict, but it's both education for vectors, so it's always a good idea to know how you can manipulate vectors strictly so that you can use it for many other purposes, right? So let's see how this sphere moves. For example, let's see. Let's check this sphere. So what I wanted to have is the point moving along the surface, and pretty much I think it is doing what I really want. It's not really going outside the surface, it's moving along the surface as much as possible. When the curvature is strong, there are chances that points are going outside like this, but as much as possible, points are staying inside the surface. So I think hopefully this is working. Another way to check is to visualize this x-axis and y-axis for each point, right, before moving. So let's disable this moving part, disable this point visualization, and to create a x-axis y-axis as an attribute, and check if these are perpendicular to each other and also perpendicular to the normal direction. So first of all, I'm going to show up the normal direction and also show up the x-axis which is the vector and y-axis. So the yellow one is the virtual x-axis, the red one is the virtual y-axis, and the blue one is the normal axis, normal direction, and everything is perpendicular. And looking at the surface, the yellow and red are, as you can see, a virtual plane which is derived from the tangent vector of the surface. So everything looks correct. All right, so I guess this is working good. It's working as I suspected. Let's uncomment, and now we have this moving points working from the surface. It's time to fix this point distortion as well, which is already looking a little bit better, but the way it distort, still using the XZ value for inside. So let's fix that to work on 3 dimension to have a bit more smoother result. Well. Okay, maybe we could also test this by not showing the lines but showing the surface itself. This is still interesting. Okay, so let's fix this. So where do we need to fix? So most of the places looks fine here. Here we are not really limiting to either axis. So these looks totally fine. Just this one, I guess. When we are multiplying to the y direction, instead of y, we want to multiply to the normal direction instead. So let's do that. So after we have moved the point position, all you want to do wait. I think we need to modify this total forces y directions instead of doing like this, because the point position is no longer on 0 for this, since this is a 3-dimensional geometry. We should modify this total force, and we only want to scale it on normal direction. Now, how do we do that? How do we do that? Let me think. I think it's pretty much the same as we have done here, but I want to make it a bit more simple. It's more like non-uniform scaling for a vector. So, okay. And in order to do the non-uniform vector, you first need to rotate the vector to one of the axes, then scale it, then rotate back to original direction. That's the easiest way to do, I think. So I am going to create the matrix 3 for the rotation using dihedral to rotate the vector from the current total force to normal direction. No. To wait a minute. Normal direction to y-axis or x-axis. Okay. Then I'm going to rotate this total force using this matrix, then scale it to x-axis, which is equal to the normal axis for now, by this multiplication only on x, and for y and z just set it to 1. Then we want to rotate back to the original normal direction. So to do that, create additional or dihedral from x-axis to normal, and rotate this total force back to the original direction. As a result, you should be able to get a better result. I'm not sure if I'm getting the right result. So let's see if I set this multiplication to 2. Okay, I think I'm getting something weird result. It's only scaling to y direction, isn't it? That's not really what I want. That's because I have this one. Damn. Okay. Make this back to 2. Okay, yeah, it's changing the height of this distortion, so I think it's working. Previously, let's have this connected here to test out the previous result. Previously, when we were changing this multiplication, it's just changing to y direction, which is not really what we want. So yeah, I think we have done the right thing. All right, looking nice or looking ugly. Okay, let's try to set some parameters for this one. Maybe we can have less number of attractors. Okay, and increase the radius. All right. Oh my god. Minimum height. controlling the minimum height, maximum height. Okay, maybe a radius a bit too much. Oh wow. And if we want to speed this up, yeah. Ooh. Okay, this is enough. Okay, so this is working on 3D for sure, I think. And if we make this back to 2D, it should still work. Yep. That is because it's generalized. It works both on 2D or 3D. It doesn't really matter, as long as you have this normal direction. All right. So this is a generalized version which works on 2D and 3D. Previously, we had only a 2D version. In order to make it 3D, you do need to do some vector math, just a small vector math, but by doing it, you can make it 3D. Okay, let's just add a select shape switching parameter to this controller and end this live tutorial, shall we? I think I'm talking too much. Okay, let's name this shape. So we have 0, 2, 1, 3. What else? What else do we have? Okay, well, yeah, that's pretty much it, I think. Okay, well, hopefully you got something new here. You have learned something new or have some inspiration or something. Let me know if you have any comments, and if not, I'll just end the tutorial live here. So as always, I am going to upload the file so that you can download the file from either from Patreon or from the YouTube description page. As always, for free, so for your reference, and just use it for any purpose. Okay, that's pretty much it. Thank you very much for watching. Yes, no. And any feedback is welcome. If not, I'll just end it here. Hopefully you found this interested. Not sure how it was. The basic idea is pretty simple. You're just moving the points based on the attractor points, and that's pretty much it. Okay, so thank you very much, and hopefully I'll be able to do another one on next week sometime, and hopefully you could also join it as well. So thank you very much for watching, and good night.